Now that we have limits at our disposal, we can finally turn our attention back to average and instantaneous rate of change. Okay, so we remember that the average rate of change takes a look at the secant line between 2 points, right? So if we have some function, let's say they look like this, go a bit steeper. And they're going down and then back up like that, okay? Recall that the average rate of change takes a look at a line like this, and of course it's not. Let's go like that, okay? So if we call this point A, then this is going to be A plus H, right? For some value of H, this is f of A, and this is f of A plus H, right? Recall from your pre-calculus, or if this is the first time you're being introduced to this, then, well, this is your first time being introduced to this, right? This is the average rate of change, right? And it's going to be given by, right, the slope of this line is f of A plus H minus f of A divided by A plus H minus A, right? That's how you compute the average rate of change between things. And in this case, our A's cancel, minus f of A over H, right? If you were looking at, between specific times here, then you wouldn't get this nice cancellation. But in the general case, we get it. So here's my question for you. If we're looking for the instantaneous rate of change, how would we find it? Okay. And one of the ways that we can think about doing this, right, is going back to our example, right? Going back to the example of this train, the way that we looked for the instantaneous rate of change was we took this limiting process as h went to 0. Now, we didn't phrase it in terms of a's and h's. We had a specific a, right? But in the general case, you have this, and you sort of slide this way, letting h go to 0, and you get this family of curves. Maybe the next one's like that. Maybe your next one goes something like this, right? Looking between this point and this point. And as you get closer and closer, I hope you can see this, you approach the tangent line, right? And this is the connection between average rate of changes and tangent lines. We first saw this concept all the way back when we were asking, well, what is calculus concerned with? And I said, it's concerned with the tangent line, which is connected to our rates of change, okay? Hopefully you can see this here, that as we let the interval over which we're calculating the average rate of change go to 0, we geometrically get a tangent line. You can totally treat this like a purely algebraic expression, right? You can take the limit as h goes to 0, that's going to shrink our interval. We can take this limit, right, for some value a, f of a plus h minus f of a over h, right? And this is going to give us the average rate of change at this value a, right? You can absolutely treat this like a purely algebraic expression, and you'll get some number out the other end that gives you the instantaneous rate of change. But again, if you look at what you're doing geometrically, this nice tangent line pops out, right? Further, what's tying us to this a, right? There's absolutely nothing stopping us from just considering the function value, right? rather than picking an individual point, just looking at, like, what is this for an arbitrary x, right? And that would speed up this computation, okay? And this idea of the instantaneous rate of change, it's so important that it is the name by which the kind of calculus we're doing gets its name, right? This is the derivative, okay? So in light of that, let's sort of formalize this definition, okay? So the derivative, highlighting it, of a function f with respect to, it's not how you spell the word respect, it's with respect to x, right? That's treating, x as our variable that is changing, is f, and then we put this little apostrophe. This is read f prime, okay? And it is f prime of x. It's just what we said. It's the limit as h goes to 0 of f of x plus h minus f of x all over h. Notice that if we were to just plug in h equals 0, we would get something that was indeterminate, right? Because this is going to become f of x minus f of x, which is 0, and h is 0. So we'll need to, probably do something a little fancy to actually compute this, okay? And with most new functions, we should think about the domain. The domain of f prime, the set of all x's for which the limit exists. And that sort of makes sense, right? Our domain, where this function is defined, is, well, it's everywhere that this guy is defined, okay? And there's a few other notations that I think you should be aware of, right? Sort of other ways that people might write them. So here's some alternate notations, right? You could have something like this, a capital D sub x of f of x, right? This is read d sub x of f of x, okay? So that's one of them. For the next one, the next two are much more common than d sub f. You can see it written as dy over dx. One thing that I want to caution you with, this is not quite a fraction. This is something a little bit different. Way you can think of it is when you see these sorts of d's like this in calculus, you want to sort of think of those d's meaning a small change, okay? So this is a small change in y over a small change in x, right? And that's what we're doing here, right? That's the process of taking h going to 0, right? That's a very small change in x and a very small change in y. That's going to give us our slope, okay? Occasionally, we'll see this a little bit later in the quarter. We'll see this guy pop up in the quarter, is my guess as well. You'll see it written as y prime. This ends up having some use when you're looking at a thing called related rates or implicit functions. We'll get there sometime next week. We'll sort of look at why that notation is useful, okay? So now we need to worry about actually computing these. A little bit later, we'll look at general rules for computing our derivative here. But in the meantime, without those, we're sort of left actually having to evaluate this limit, okay? And it turns out, generally you can break this up into either a two-step or a four-step process. Okay, the book breaks it up into four. I prefer to break it up into two steps. Okay, but let's look how to actually compute. Okay, so the four-step version goes like this. First, you compute f of x plus h. And I will color code these for us. 2, you compute f of x plus h minus f of x. Okay? We're going to compute, or rather form f of x plus h minus f of x over h, and then finally we compute our limit as h goes to 0 of f of x plus h minus f of x over h. Okay. When I say I prefer to do it in two steps, usually I find it simpler to just do steps 2 and 4, right? And sort of let steps 1 and 3 happen along the way. But let's jump into a couple of examples. Okay. So our first example, we'll take a look at let's say f of x equals 3x plus 5. Okay. So our first step, we want to calculate f of x plus h. And as you saw in your homework, to do this, everywhere we see an x, we're going to put an x plus h, right? So 3x plus 3h plus 5, okay? Second, we're going to go f of x plus h minus f of x. We already have an expression for f of x plus h, so we can copy it down, 3h plus 5, minus our f of x, so 3x, and then this is the thing to pay attention. We have minus 5 here, right, because we're subtracting this whole thing, and we get some nice cancellation, right? Looks like our 3x's are going to cancel and our 5's are going to cancel. So we're going to have 3h, okay? Third, we're going to divide by h, so 3x over h, right? And then finally, we're going to compute our limit as h goes to 0, f of x plus h minus f of x all over h. Since we're taking the limit, right, we can cancel these h's no problem. And we're just left with the final answer of 3, right? And so notice that this 3 exists regardless of our input x, right? But that should make sense, right? Because 3x plus 5, well, 3x plus 5 is just a line, right? Probably looks something like that. And on a line, the average rate of change is constant, right? And since the average rate of change is constant, doesn't really matter whether we're looking at the average rate of change or the instantaneous rate of change, because for that whole limit, it's constant, okay? So let's go to something a little bit more involved, right? Let's look at our old friend f of x equals x squared, okay? So the first thing we're going to take a look at is x plus h, right? So x plus h squared, we're going to get x squared plus 2xh plus h squared. Okay. Taking our difference, looks like we're going to get x squared plus 2xh plus h squared minus x squared. We're going to get some cancellation here. It's going to become 2xh plus h squared. Okay. 3 x plus h minus x over h. I'm going to factor out an h like this, 2x plus h over h. And that way, when we take our limit, what are we going to get? Minus f of x over h. Well, these guys are going to cancel. After those two cancel, we're left with a limit as h goes to 0 of 2x plus h. The limiting process on h does not affect 2x at all. It does affect the h though, right? This h vanishes and becomes 0. And we're left with a total of 2x. And so that tells us that our instantaneous rate of change, right, the slope of the tangent line of x squared is 2x, right? If you pick some point on your parabola, say x equals 2, right, then the slope of the tangent line tangent to x squared is going to have a slope of 4, okay? Let's make this one a little bit more complex, right? Let's take a look at x squared minus 4x, right? And what I want to note to you here is we have no reason to think that our derivative will break over addition and subtraction. With such a convoluted definition as this guy right here, given just this, we have no reason to think that you can break it up like that. So we're sort of forced to, I guess, continue the old-fashioned way. For this one, I'm going to skip to steps 2 and 4. So we're looking at f of x plus h minus f of x, right? So we're going to have x plus h squared minus 4 times x plus h, right? This is our first term. And then we're going to subtract from that f of x, which is x squared minus 4x. Expanding this square here, we see we get x squared plus 2xh plus h squared. We're subtracting 4x, we're subtracting 4h, we're subtracting x squared, and we're adding 4x's, right? Now we want to simplify. And what do we get post-simplification? Well, my x squareds are going to cancel. I'm left with 2xh. My h squared doesn't cancel with anything either. My minus 4x and my plus 4x cancel. And then we're left with minus 4h. Okay? In step 4, we're taking the limit as h goes to 0 of f of x plus h minus f of x over h, right? This is our derivative itself. And what's that going to be? Well, we're going to have 2xh plus h minus 4h. This should be h squared. All that's being divided by h. We are taking the limit, so I can't forget that. Right. I can factor out that h from the whole top. That's what it's going to be 2, or h times 2x plus h minus 4 over h. Canceling those h's, I can straight evaluate the limit then. This h is going to become 0, and there's no h's in either of these. So we can say that f prime of x is 2x minus 4, okay? And there's a couple of questions that I want to consider here. Since we have this line being the slope of our tangent line of this parabola, what happens and where does our derivative equal 0? Okay, and this derivative equals 0 when 2x minus 4 equals 0. So that means our derivative equals 0 when x equals positive 2. If you were to complete the square on this guy, you would get x minus 2 squared minus 4. And what that would tell us is that our function has a, or rather has its minimum, has its vertex at the point 2, 4, 2, negative 4, right? This is a very, very admittedly rough sketch of our graph, but it's going to look something like this. And here's what I want to draw your attention to. This is a point that we will explore in detail sort of throughout the quarter. It's one of the reasons that our concept of a derivative ends up being very, very important. But this is our tangent line, right? Our tangent line at x equals 2 is this line right here. That's where it equals 0. Notice that's the exact same place where a minimum occurs. Okay, and like I said, we will draw out what exactly that means and why it's important later, but it is a concept that I want to draw your attention to. Okay, next let's take another look at computing the derivative. This time, let's look at the derivative of 1 over x. Okay, jumping to step 2, we're looking for x plus h minus f of x. Okay, what is f of x plus h? Well, that's going to be 1 over x plus h. Okay, and we want to subtract from that 1 over x. And in order for this expression to be at all useful, right, we're going to need a common denominator. Well, we can multiply this guy by 1 over x, or by x over x. We can multiply this guy by x plus h over x plus h, right? And that's going to give us what? Well, we're going to get x minus h over x times x plus h. Or, if you prefer, canceling those x's, h over x times x plus h. Okay? Jumping to step 4, our derivative is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. Okay, we have our expression for this, and how does it simplify? We're taking our limit as h goes to 0. I'm going to actually break out this 1 over h minus h over x times x plus h, right? These two are going to cancel, okay? And then what are we left over with? The limit as h goes to 0 of minus 1 over x times x plus h, right? Here, we can simply evaluate this limit, right? It's no longer indeterminate. As h goes to 0, this expression is just going to become x, right? And our derivative is negative 1 over x squared, okay? And we can use this to compute all sorts of tangent lines and all the things like that, okay? At home, this is what I want you to do, okay? I don't want you to just find the slope, but actually find an equation for the line tangent to f of x at x equals 1, right? We have the equation for the derivative. Find the derivative at x equals 1, and then go through the process of actually finding the equation for that tangent line. So for our next example, okay, say say that your weekly demand for, I don't know, maybe you're selling tires today. And say that it's modeled by P of x is 144 minus x squared, okay? Where P, right, is our price per tire measured in dollars, and x is measured in 1,000 units, right? So if our quantity demanded is, say, 1,000 units, then it's going to be $134 a tire. And we're interested in finding the average rate of change, and then the instantaneous rate of change, okay? So first we'll take a look at the average rate of change. In this case, the rate of change is going to give us the relationship between how price changes based on demand, okay? But we have an expression for our average rate of change, right? It's going to be f of x plus h minus f of x all over h, right? And then you could pick your favorite values of x and h to give you your starting point and how much you change it by. Computing this, right, we see f of x plus h is going to be 144 minus x plus h squared, right? And that's all being subtracted by 144 minus x squared, and we're dividing by h, right? Expanding this, we see 144 minus x squared minus 2xh minus h squared minus 144 plus x squared over h, and then simplifying, our 144's cancel, our x squareds cancel, we have minus 2xh minus h squared over h. This h is going to cancel with that h and one of those h's, and we're going to get minus 2x minus h, okay? So if you were looking, for specifics, right? If you were looking for the average rate of change of our price, between 5,000 tires and 6,000 tires, you could take x to be 5 and h to be 1, and our average rate of change is going to spit out negative 11, which means when you increase by 1,000 more tires in the demand, the price is going to drop $11 a tire, okay? But let's take a look at the instantaneous, right? Let's see if that tells us anything more, okay? Let's take the limit as h goes to 0 of f of x plus h minus f of x over h. We already have an expression for this, right? So we're looking for the limit as h goes to 0, it said minus 2x minus h. This h is going to vanish, and there's no h's here, so we're going to get minus 2x, right? So that means that the instantaneous rate of change at any given point along our demand curve is going to be negative 2 times whatever that point is, okay? So if you increase your demand, you're going to decrease the price. If you decrease your demand, you're going to increase the price, right? This fits with what we expect, right? If you were to graph this 144 minus x squared, you'd see something like that, okay? And this idea of a negative tangent line, right? It fits with what we would expect, okay? One last thing that I want to draw your attention to, and before we wrap it up for the day, is two sorts of functions that are going to sort of mess with the tools that we've created. And they're functions that look like this, and functions that look like this, okay? Both of these are indeed functions, right? And we'll call this point A, and that's f of A. And likewise, we'll call this center point right here A, and this point f of A. And there's two problems here, okay? These are separate problems, and so let's take a look first at this guy, okay? Now, we found our derivative by looking at secant lines and taking their limit as the interval over which we found that secant line went to 0, okay? And in particular, right, we only sort of considered forward change. Didn't quite mean to erase that, but we can draw it back in, right? Now, if we only consider positive values of h, right, we would seem to get to, or at least to be able to get a tangent line, something pretty steep like that. But here's the problem. Our limits here aren't one-sided. H can absolutely be negative. But if we take the left-handed limit here, right, sort of approach from the left, our tangent line is going to be a straight line like that. And these two disagree. So our limit does not exist here. And since the limit doesn't exist, the derivative doesn't exist, right? And that's purely based on the fact that right here, right, we have this sort of sharp turn right there, right? There's this point, abrupt change, sharp turn, whatever you want to call it. This is a problem for our derivative, okay? Let's take a look at our other one and see what happens as we approximate it with secant lines, okay? First one might look like this. Right, since I'm zoomed in, I'll make our line a little bit thinner. As we approach, we might get, not sure how that happened, should be there. As we approach, you know, we might get something like that. Then we might get something like that. And if you'll notice, the line we're approaching here is vertical. And this is a problem, right? Because when we have a vertical line, it doesn't have a defined slope, right? Vertical lines have no slope, horizontal lines have 0 slope. And since our line has no slope, we can't dream up anything called a derivative because, well, the derivative is the slope of that line, okay? So we can't do anything here, right? We can't define a derivative in either of these cases. This one because we have a sharp corner, right? This one because our slope is actually undefined, okay? And it's with this idea that we actually go back to continuity, okay? If we look at both of these, right, our function it's not differentiable everywhere, but it is continuous. The function does equal the limit value at each of those points, right? Our functions are continuous, but they're not differentiable, right? So what that tells us is that just because a function is continuous doesn't necessarily mean that it's differentiable. However, this will be very useful for us. The other way is true. If a function is differentiable, then it is continuous, right? A thing to note here, right, is our definition of a derivative, this limiting process with the secant lines, it only makes sense if our function is continuous, right? So the fact that differentiability implies continuity is huge, okay? And now we can sort of take our sketch from the end of the last part of this lecture and fill it out with more things that are problems for us, right? So let's say we have a function that does something like this. It goes like that, and it jumps up here. Maybe there's a hole right there. Maybe there's another hole right here where it's defined up there. Maybe it zooms off to infinity right there with a vertical asymptote. Right? You can make this guy, nice and not very well behaved. Maybe we go like that with that sharp corner, and then do something like this. Okay, how many bad points? Let's see, we've got 1, 2, 3, 4, 5, 6, and then 7 right there. Okay, and let's go over again why each of these are bad and sort of what they're called, right? This guy right here is called a jump, right? We're going along this way and then we're jumping up here, right? Here we're not continuous, so we're not differentiable. That's a hole, right? It's just a simple hole in our graph. Not continuous, so not differentiable. This guy here at C is also a jump, right? We're going this way, we're jumping up, and then we're continuing. This guy is a one-sided vertical asymptote, right? It's not continuous, so it's not differentiable. But then now that we get to the other side, things start to change a little bit, right? We're definitely continuous here. I'll actually put this up here. But we have a sharp corner, both at E and at F, right? And at these sharp corners, again, our function is continuous, but it's definitely not differentiable, because what's the derivative? Is it that or is it that? Is it that or is it that? We can't dream up how to define a derivative there. And then here, our tangent line is vertical at our point G, right? And so our derivative isn't defined there either, okay? That's going to wrap it up for this lecture. Come back Thursday and we will look at some specific rules for computing the derivative, so we don't have to go through this brutal limit calculation every time we want to find a derivative.